Last time we talked about basis expansion, which is a way to fit nonlinear function between pair data x and y. But the big limitation for that is we have to make specific assumption about function f. So this time let's talk about cubic spline to see how we can do this without making any assumption about function f. Okay, so the problem setup, we are starting with pair data xi and yi, where I goes from 1 to n. For cubic spline, the relationship between x and y actually have no noise in it. So usually, for the regression problem, we have the epsilon I term here as a noise. But for the cubic spline, it is not really a statistical method. It's more like an interpolation method between data points. So let's just get rid of the noise term. No noise. And for the next time, we are gonna look at the smoothing spline, which build upon on cubic spline. That is a statistical method, can handle noise. But this time, let's talk about cubic spline. Okay, so geometrically, what this means is that let's say that we have some data points. The idea is to find a curve that interpolate all the points, and that the curve must pass through all the points. So that's what we mean by no noise. I should also note that let's also sort the data such that x1 smaller than smaller or equal to x2 to xn. So this is a sorted data. So the question is that how do we find this curve that interpolate all the data points? And probably a simplest way that we can think of is that we just connect all the points. Okay, so how about let's just define a piecewise linear function. That's like the easiest method we can think of. So idea one is that piecewise linear. So let's say here's our points, and then we just connect those with straight lines. But this is probably not a very good solution, right? Because the function is non-smooth. Fx is not smooth. This is So what does non-smooth mean? Is that it means that the first derivative of function f is not continuous. So if we want to draw the first derivative of this thing, it's going to be up, down, and then up. That's not continuous. So that's why this piecewise function has that zigzag shape. And we certainly don't want that. We want our curve to be smooth. And so how do we improve this idea? Well, we can make this well. The simplest thing is that we can keep going and then make our first derivative continuous. So this is the idea two, and so we can do a piecewise quadratic. Quadratic cannot bend like this. It's gonna and then do this. And that's way, if we do this, then the first derivative of this thing is going to be a piecewise linear function. And it's going to look something like this, right? It goes down, and then now it's continues downwards. Okay, and then continues downwards, and then goes upwards. So that's going to be our first derivative. It can be continuous. So that's why this curve looks much better than the piecewise linear. This is f prime of x. And but the problem for this is that if we look at the second derivative, that's going to be a piecewise constant function. It's not going to be continuous once again. You have something like this, right? That's This is going to be f prime prime of x. That is not continuous. So this is actually this is a limitation for the piecewise quadratic. It's because the second derivative tells us how the curve is going to bend. It has to do with the curvature of the curves, and if it's not continuous, like there are parts that's going to be the quadratic function is just too it's just it's just not flexible enough to do this task. It is much better comparing to the piecewise linear function, but we want a little bit more than that. We want the second derivative to be continuous as well. So this really brings us the idea of cubic spline. Is that we want to make a piecewise function with continuous fx, f prime of x, and f prime prime of x. So we want both the first and second derivative to be continuous. That's when we have a very smooth fit of the curve. We cannot see it, see the curve. For our eyes, we cannot tell where the curve has those awkward turns. So that's really the idea. And I should emphasize that this case, the fx is cubic. The f prime of x is going to be quadratic. And the f prime prime of x is going to be linear. Okay, it's going to, and they are all piecewise functions. So that means I can write down the function in this form that f of x equals to f1 of x all the way to fn minus 1 of x. So each piece is going to be a cubic function that this is going to be a1 x cubed plus b1 x squared plus c1 x plus d1. That's the general way we write the cubic function. So this is n minus 1 x cubed plus b n minus 1 x squared plus c n minus 1 x plus d n minus 1. So this is where x is, sorry. So we just define it for each segment. That means like if our curve, this is our curve, and then here we have 4 points. That means there are 3 segments. So each of the segment here, we're going to define a different function. This is f1 of x, f2 of x, and then f3 of x. And each of the piece will be a different quadratic function with different coefficient. And let me just spell it out. So the first segment is x going to be in between x1 and x2. And the last one, x is going to be in between xn minus 1 and xn. So that's how we define the cubic spline function. And also the other condition I didn't write here is that we want f of xi equals to yi for all I. We want the curve to pass through all the points. Okay, so now let's see how we can solve this problem. So for that, to solve this problem, let's actually consider an easier example here without loss of any generality. So let's only consider 3 data points. So we're gonna and let's set our x to be -1, 0, and and 1, y3. So only 3 data points, but this is totally gonna work if you have like random x as intervals and then you have n data points. It is the same math, but for the simplicity, let's just look at this easier example here. So this means that we have 3 points. And then we're just gonna see what is the best curve that can interpret the data with cubic spline. Okay, so let me just write it out let me just write it out the explicit form for this function. Then this function really here has 2 pieces. Okay, f of x equals to a1x cubed plus b1x squared plus c1x plus d1. Now this on a2x cubed plus b2x plus c2x plus d2. Okay, this is x. So that's our piecewise cubic function. You see here we have 8 unknown variables, a1, b1, c1, d1, then a2, b2, c2, d2. So we have 8 unknowns. That means like we need to solve these 8 variables. Let's see if we but we have constraints, right? Let's just spell out all the constraints to see what we're gonna get. So the constraint for this, the first constraint is that yi equals to f of xi. We need to pass through all the points. That means there are we have 3 data points. So y1 equals to f minus 1, y2 equals to f0, y3 equals to f of 1. This gives us 3 equations. The 3 equations gonna be um, it's gonna be a minus a1 plus b1 minus c1 plus d1 equals to y1. And then the second one is going to be, this is easy, it's going to be d2 equals to y2. And then the third is going to be a1 plus b1 plus a2, b2, c2 plus d2 equals to y3. Now we have 3 equations from here. And so the second constraint we have are just the continuity constraint, right? We have so fx continuous, but here since we only have 2 segments, so we only need to care about the middle point. That means this means that at this 0 point here, we need to make f continuous. So that means this means d1 equals to d2. And then for the third one, next constraint is that f prime of x need to be continuous. Uh, okay. So let's just do the derivative of f prime x first, right? So f prime, let me just write it over here. F prime of x equals to, we just take the derivative of this thing, that's going to be 3a1x squared plus 2b1x plus c1, and then 3a1x plus 2b2x plus c2. Okay, let me just see, let me just grab this thing over here. Okay, so now you can see this clearly. And then that's the first derivative, and then the second derivative, we can get that, graph that as well. We can use that soon. That's going to be 6a1x plus 2b1, then 6a2x plus 2b2. So these are the the first and second derivative. And then to make it continuous, we only need to care about the breaking point, that is at x equals to 0. So that's going to be, we just plug in 0 here, we got C1 equals to C2. And then the f prime prime continuous is going to give us B1 equals to B2. 2B1 equals 2B2. We can just cross out the 2. Uh, so we got B1 equals to B2. Okay, so now let's see. We have in total of 6 equations now, but remember we have 8 unknowns. Okay, so that means we need 2 more equations. And that's so for cubic span, we already also define the boundary conditions. The boundary conditions for this the boundary conditions usually we defined it as this, as f prime prime of x1 equals to 0. We want the second derivative to vanish at the boundary. Also, f prime prime of xn equals to 0. So we translate this, and we can get 2 more equations to be this, to be we plug in -1 here, it's got minus 6a1 plus 2b1 equals to 0, and 6a2 plus 2b2 equals to 0. That's going to be our last 2 constraints. Okay, now and let's just let me just show you the full picture here. Okay, so we have 8 unknowns and 8 equations. So that means we can solve this problem. And the nice thing is that everything is linear. This is a linear system. It can be easily solved if we just turn everything into a matrix, into a giant matrix. And let's see how we can do that. We can definitely solve this with by writing everything down in a matrix form. So this is going to be so here we're going to put our parameters in a1 b1 c1 d1 a2 b2 c2 d2. So so that's going to be this is going to be a times 1 vector, and then you know I'm not going to write out the full thing, but you can definitely translate like each of the equations, just putting the corresponding number into here, and then you know, and then solve this as a linear system. That's how we solve the coefficient for the cubic spline. Okay, maybe I can do one. Okay, let me just translate the last equation here. Let me just translate this one. So we have that means we have 4 zeros and then 6 and a 2 and a 0 0. So that's gonna, this vector here, this row vector is gonna multiply this column vector to give out the last number to be 0. Okay, we can write this whole thing out and solve it as a linear system. So this is how we solve, this is the idea of how we solve the cubic spline. And if we have n variables, let me just write out the number of equations to make sure everything works. So if we have n data points, then that means we have n minus 1 segment. And this means that we have 4 times n minus 1 coefficient. These are unknown parameters we want to solve. And let's talk about the constraints. So constraint first we have yi equals to f of xi. That's because we have n data points, so there are n equations. And then the second set of things is that we want fx to be continuous. Fx continuous, that means at each of the breaking point in between, we're gonna we need to equal the function from left or right, right? So when we have n points, that means there are n minus 2 points in between. So that gives us n minus 2 equations. And then f prime continuous, that's also n minus 2. F prime prime of x is continuous. That means there are n minus 2 equations. And the third is at the boundary conditions. These are 2 equations. If we just sum this thing up, what we're gonna get is that it's n plus n minus 2 times 3 plus 2 equals to 4n minus this is minus 4. Okay, so that is this is the same as the number of coefficient. This is 4 times n minus 1. So that's we have the same number of unknowns, and then as the number of equations, that means this is a full linear system we can solve. Okay, so that's actually that's everything about cubic spline, and but you'll see that you'll probably see this from the very beginning of the video that cubic spline cannot handle any noise. So this is not really a statistical method, and so what happens is that the limitation is that it has to pass through all the points. So suppose we have a very dense point like this, and then the cubic spline is going to interpolate every small term of this. It's going to interpolate every small term, so that make it a pretty bad model for statistics. So this is lead to the problem of overfitting the data. The second limitation is that this is a one-dimensional interpolation method. This means that if we have like multi-dimensional X, it's just simply not going to work. 1D method. So these are the problems we're gonna address in the upcoming videos. And for the first problem, overfitting, next time we are looking at smoothing spline, where we don't enforce every point to pass it through y. Okay, where we don't enforce a curve to pass it through every point. So that's how we solve the overfitting problem. And for increased dimension, if we want to do this on multiple dimensions, we're going to introduce kernel functions and then to see how do we rewrite everything using the kernel functions for the smoothing spline.